Alright, so here we have a 6 kg box that is being pulled across a rough floor by a constant tension force of 24 newtons. It says it is being pulled for 6 seconds and the speed increase from 0 to 20 meters per second. Alright, so here we have a diagram of a box of mass 6 kg is being pulled. As shown here in the diagram, there is an opposing force F of K acting against it pointing leftward. Alright, other than that, let's go ahead and crack it up. A, B, C, D, and E. Part A asks us to find the average speed during from 0 to 6. So here is a velocity time graph that goes with this particular diagram. Well, here to find average speed, you have a couple of different options. So I'll just start with the traditional average speed is just distance over time, or total distance over time. But as you can see here, the object moves one way, it's just being pulled to the right. So nothing to add here. All right, and that you're given a velocity versus time graph. So the first thing, hopefully, you should have in mind or recognize is that the area beneath the velocity time graph is your displacement. But this one's pretty easy. The whole entire graph is above the t-axis, so it's telling you that the object is moving rightward. So in this case, if I find the area, that tells me my displacement, which is a vector. However, the magnitude of that displacement is my distance. So I'm just going to find the area here. I think this is the quickest strategy to do. So here, the area of this particular shaded triangle, it is a right triangle, so we can just do 1/2 times base times height. Base being 6 from 0 to 6 seconds, and then all the way up is your height being 20 because on the graph it said so. So 1/2 times 6 times 20, that'll give you an area of 60. So once again, the area beneath a velocity versus time graph is your displacement, and the magnitude of that displacement is your distance. So here, I know what D is, I know what T is. D here being 60 meters, T being 6 seconds, because it says so in part A. And other than that, you're done. 60 meters divided by 6 seconds will give you an answer of 10 meters per second. Average speed is a scalar, so I don't need to provide any sort of direction, so I'm done there. However, if you wanted to, you can also recognize that because the box is moving one way, that this particular function for kinematics is also solid. V average, even though this is V, which is a velocity, you can use it just to find the magnitude, okay? Because average speed is just the magnitude of this stuff. All right, here, I know VI is 0 because the graph said so, and it says so, okay? Anyways, here's VF. VF here is, what is it, 20? And the graph shows that it speeds up to 20 meters per second in a time of 6 seconds. Other than that, I'm done, really. I have VF, which is 20. I'm going to divide it by 2. So plugging in VF is 20 divided by 2, and the answer is still going to be 10 meters per second. So once again, even though this is the average velocity function, I'm just going to give you the magnitude, which is just 10 meters per second. Now, if it asks you for average velocity, you can do the same process, except in this case, just put a positive sign in front to indicate that it is a vector. Okay? All right, so the answer is still 10 meters per second. Part B, I asked you to find the magnitude of the kinetic frictional force, F of K. So here goes magnitude. Well, to find F of K, I'm just going to set up my Newton's second law. Net force equal to ma. Here I have T pulling right in the diagram. F of K is pointing leftward. So I'm going to say T minus F of K is equal to ma. Other than that, I'm just going to crack it out to get F of K by itself because it asks you to find F of K. I'm going to go ahead and do a little algebra first. I'm going to move this negative F of K to the right side, and then MA to the left side, so change signs as you move them. So MA, that's positive on the right, becomes negative on the left side here. Negative FK becomes positive once you move it. Here, I know what T is. T is 24 newtons, is given in the statement. Here's 24 newtons. And then M is 6 kg, that's also given in the problem. The only thing that I don't know is the acceleration of this particular system, but I can find that pretty quickly. You're given a velocity versus time graph, right? So you should know also that the area is delta x, but the slope of a velocity time graph is your acceleration. So there's a lot of information that you can pull out of a velocity versus time graph. You just have to know what to do. All right, other than that, here acceleration is just the slope of this line, and the slope in this case would just be change in velocity over change in time, or really just rise over run. But as you can see here, if you look at the diagram correctly, from 0 to 6 seconds, that's your run. So my answer in the denominator is 6 seconds, and then my rise is from 0 to 20. So the change in velocity here is 20 meters per second during that 6 seconds. So change in velocity here is just 20 meters per second. Change in time here is just 6 seconds, and I'm going to leave that as is. Okay, you can reduce it if you want. I'm just going to leave that as is. So here, I'm just going to carry that particular answer down. So I found that the acceleration is just the slope, which is just rise over run. And then I'm just going to go ahead and take that 20 over 6 down here. So I'm going to substitute out A for 20 meters per second, 20 meters per 6 seconds square. And I'm just going to go ahead and cancel the 6 and 6 out there. And that leaves me with just 24 newtons minus 20. And then that's equal to F of K. Other than that, you're done really here, right? 24 minus 20 is just 4. And this is just a magnitude. So if it doesn't use the word magnitude, you would have to make sure you put the answer as a -4 because the arrow itself is pointing leftward. But because it asks for magnitude, I'm just going to go ahead and say that the answer is 4 newtons. And I'm done with part, what is that? B. Okay, all right, let's crack out C. C asks us to find the coefficient of kinetic friction. The coefficient of kinetic friction here is just, by definition, the ratio between F of K and F of N. We already found F of K in part B. F of K here on the screen is 4 newtons. But what I don't know is I don't know F of N. But this one is pretty straightforward. Here, F of G is pointing down on the screen here. I'm just going to draw my free body diagram in the vertical direction. The floor is going to push up on the box, and therefore that's the contact force there. That's F of N. And there are only 2 arrows here in this particular diagram in the vertical direction. So I can say that Fn has the same magnitude as F of G. So therefore I'm just going to go ahead and substitute that out or that in for the statement here. So Fk in the numerator stays the same. Fn though, I substitute out for F of G because the magnitude is the same. And then I know the definition of F of G is mg. Well, here I know mass, I know G, I know Fk, so really I'm done. Fk is 4 newtons. M times, what is it? M is 6. 6 times 9.8 is 58.8. And then here, the coefficient of friction has no units and it has no direction. So other than that, I am done here. So the coefficient here is just 0.068. Okay, so that knocks out A, B, and C. Let's go ahead and crack out D and E. D asks you to find the work done by the applied force T. So it says done by the applied force T, so I'm just going to focus my attention on the tension that's pulling the box to the right. Okay, so I'm just going to apply the definition of work. Work by definition is the force that's parallel to the displacement. In this case, T is indeed parallel to the floor because it's not angled down or up. So therefore, T is already good to go. Here, T is 24. And then I'm just going to use my answer in part, well, not my answer, but one of the things I calculated in part A, which is the area here. The area beneath a VT graph is my displacement. So during 6 seconds, I found the displacement already to be 60 meters. So I'm just going to go ahead and use that value. That's where the 60 came from. So delta x is just 60 meters because I'm using the whole time interval. All right. Other than that, just calculate work. 24 times 60 is 1,440 joules. And that is it for part D. That's pretty light work. And then E asks you to determine the net work on the system. So notice here it says net work. So you do have to consider all your forces. So here you have T pulling right. You have FK pulling or acting against it, pointing leftward. So here I'm just going to set up the same stuff here. However, I'm just going to say net work is equal to net force times displacement. Well, net force in this case would just be 24 newtons, which is T, minus 4, which is F of K. And once again, T is 24, Fk we calculated, which is 4. So I want to subtract those two because they're opposing. So here in parentheses, I have 24 minus 4 times displacement, once again, is 60. Other than that, 24 minus 4 is 20, and then 20 times 60 is 1,200 joules. Okay, so even though you're putting in 1,440 joules, really the system is only gaining about 1,200 because there's energy loss due to friction. All right, here the other way to do part E, if you want, is to use the work-kinetic energy theorem, which I like a lot because I think it just sometimes expedite problems here. So the net work is the change in kinetic energy. Here, I can break up Kf minus Ki. I want to cancel K out because the graph says that the object starts at rest, because the graph starts at 0. Other than that, I'm just going to break up Kef into 1/2 mvf squared. Well, I know what m is. M is 6 is given. And then Vf here is going to be 20 for the graph, okay? Because the graph says that after 6 seconds, it reaches a speed of after 6 seconds, it reaches the speed of 20 meters per second. And I'm going to square that. So really, I'm going to do 1/2 mass of 6 Vf here at 6 seconds is 20. I'm going to square that. And if you plug that on your calculator, you get the same answer, 1,200 joules. Okay. Other than that, I'm done. Stay nerdy. Don't be whack.